Hi, welcome to the second part of the counter design lecture. And in the in last lecture, what we did, we have discussed the regular counter, okay? And in this lecture, okay, we will discuss the irregular counters, okay? And as we have done with the regular counter, we'll talk about how we design irregular counters using the general sequential design process or procedure, and we'll talk about a simplified method. Okay, um, we will present three examples. Okay, so just a matter of review here. We know that regular counter. Suppose I have three flip-flops, Q2, Q1, and Q0. We said regular counter counts from 0, 1, 2, 3, 4, 5, 6, 7, and then it goes back to 0. Notice I started from 0 all the way here to 2m minus 1, okay, where m uh, is number of flip-flops, okay? So I went from uh, 0 all the way to 2m minus 1. And here m equals 3. Okay, so 2 to 3 minus 1 is 7. So this is and going through steps of 1 here. So this is a regular counter. Irregular counter violates the rule of not going, for example, to maximum number of 2 to them. So we'll look at example 1, where we have a counter we call it mode 6, which counts from 0, 1, 2, 3, 4, and 5, then goes back to 0, da da da, and continues. So notice absent here is 6 and 7. So we don't go through 6 and 7. Okay, that's why it's irregular. Example 2 of irregular counters that we will discuss starts at 2, 3, 4, 5, 6, and then it repeats 2, so on and so forth. So absent here is 0, 1 at the beginning. 0, 1 is not present, and 7 here is not present. That makes it irregular counter. Look at example 3, where we count 2, 1, okay, 4, 3, 7, random, and then we repeat 2, da 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 da. So this is more of a random. This is example 3, random counting. So we'll look at those from the perspective of general purpose, and then we will present a simplified design procedure for irregular counter. And then finally, we'll talk about a third topic, which is frequency dividers. That's a small final topic. Okay. So at the end, so because this lecture covers regular counter, irregular counters, and frequency dividers at topic 3, which is a small and the last one. Okay, so let's start with irregular counters. Okay, all right, and we'll start with example 1, where we'll do the general design procedure of the sequential circuit. Okay, okay, so let's see that we want to um, design an irregular synchronous counter, which counts the following sequence: um, 0, 1. Okay, before that, we will design mode, we'll call it mode 6 counter. So it counts from 0, 1, 2, 3, 4, 5, and we stop at 5 because you cannot reach 6 or exceed it. So then we repeat 0, da 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 da. So this is a repeat. So as we said in the intro, that this is irregular counter because it doesn't continue all the way to 7. So let's get into the very first step with the general design process of sequential circuits. We have to construct the state diagram. So obviously, before I state diagram, let's think about how many flip-flops I need. Well, 1, 2, 3, 4. So so here we have 1, 2, 3, 4, 5, 6 sequence. Okay, so suppose I don't know, I apply the mathematical equation log of 2 of 6 and take the ceiling. That will give us 3 flip-flops, and so we'll need 3 flip-flops, and let's assume we will use T flip-flop. Okay, let's assume that we will use T flip-flop. Okay, now let's construct the um, the um, state diagram. So 0, 1 clock, we go to 1. 1 clock, we go to 2. 1 clock, we go to 3. 1 clock, we go to 4. 1 clock, we go to 5. 1 clock, we go back to 0. Okay, so this is the state diagram. Now, the next step is to construct. So state diagram is to construct state table. Okay, all right. So state table. Let's um, draw our state table here. So first we have our what? Present state. Present state. Okay, here we have Q2, Q1, Q0, and then we have next state. Next state. We have Q2, Q1, Q0, and then we have the input to the flip-flops, T2, T1, and T0. Okay, let's construct the lines of the table. Okay, so now, so let's try to fill the table. Okay, and we'll use the red color here. So if I'm state 0, 0, 0, next state will be what? 0, 0, 1. If I'm state 0, 0, 1, next state will be 2, which is 0, 1, 0. If I'm in state 2, I'm sorry, 1, 0, 2, I'll go to state 3. Okay, if I'm in state what? 3, I'll go to state 4. Okay, if I'm state 4, I'll go to state 5. If I'm in state 5, I'll go to state 0. Okay, so watch that, 0. Okay, well, if I'm in state 6, where do I go? Whoops, sorry. Well, we are not supposed to go there. So this is next state will be a don't care condition. I see. So this is interesting. So what about if I'm in state 7? Well, you are not supposed to reach state 7. So it's a don't care condition. We don't tell you, we don't care. Okay. So notice that these states that are unreachable state, they're unreachable means we will not reach 6 and we will not reach 7. By design, the counter shouldn't go to 6 and 7 because the state diagram says so. Okay, because I'm designing my counter so that it doesn't reach 6 and 7. So the next state for them will be don't care. So what will be the T1 and T0 values? It will be as well do not care. And that will help my K-map, by the way, right? Okay, so now let's construct the um, the T inputs. So we know that if we change one, if we don't change, so if the present state to next state change, the T will be 1. If they are the same, T will be 0. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1. Okay, so this is for T2. Let's go T1 now. So 0, 0, 0, 0, 1, 1, 1, and 1, 0. Okay, 1 and 0, 1, 0 and 0, 0. Okay, and 0 and 0, 0. Okay, um, let's go to T0 now. 0, 1, 1, 1, 0. That will be 1 and a 0 and a 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1. Okay. All right, let's simplify now the equations for T0 and T1. So after working K-maps, so we'll do this quicker because now we assume that you know how to do it in K-maps. We will say that T1, T1, it's clear, T1, I'm sorry, T0 equals 1. Okay, how about T1? If you go through the K-map, T1 should equal Q2 prime and Q0. Q2 prime and Q0. Okay, so if you plug in these values in K-map, I hope you did not forget the K-map. Okay, and T2 equals, okay, Q2, Q0, Q2 ANDed with Q0, or Q1, Q2, Q1. Okay, and to simplify it more, we say take a Q2 as a common factor, and then you have in between here let's see if I have oh, this will be a, so this will be a Q1, Q0, okay, and so a Q that we will take a Q0 common factor. So let me repeat this again, or just do a quick erase here. So here, okay. So let's go back to the pen. Okay, so now this is equal to Q0 ANDed with Q1 plus Q2. Okay, that's T2. Okay, so let's draw the circuit now. So we have the following flip-flops. Okay, the following flip-flops. Okay, so we have T1. So this is T, Q. We have another flip-flop here, T, Q, and a third flip-flop we have here T and Q, and this input here is T0. This output here is Q0. This is here T1, and this is here Q1. Okay, this is here T2, and this is here Q2. Now, we add the gates now for this thing. So how about T0? Well, T0, let's use this color. T0 is obviously 1, so we connect to T0 a 1. How about T1? T1 is Q0, Q2 prime. Okay, so we'll connect it from here. Okay, so this is an AND gate. Okay, and we'll take a bubble from here. Okay, because this bubble will be Q2 prime, and this is going to be connected to T1. Now, for T2, okay, so for T2, we'll avoid connecting the lines to make it simpler for us. So we'll have um, Q2, Q1, and Q0, and this will go to T0. Okay, so, and then finally, do not forget for your flip-flops to add the clocks. Here is a clock, CLK, and here's the clock, CLK. Same clock because this is synchronous design. So this is now a design of irregular counter, which counts the sequence 0, 1, 2, 3, 4, 5, then 0, 1, 2, 3, 4, 5. Okay, so this is here, we have a bubble here for Q2. All right, so this was example 1. Okay, let's move to the next 2 examples and we'll do them very quickly. We'll probably do it at the state machine level and then the continuation process. Now you are very familiar of the steps. First step is state diagram, state table, minimization of the equations, okay, and then finally the circuit. So that's now should be very clear in your mind when you are going through these questions. Okay, so especially this is what we're referring to the general design procedure or process for sequential circuit. Okay, so let's go now for another example here. And this second example here should talk about the uh, uh, counting sequence that we said, excuse me, we have uh, a counting sequence um, that counts 2, 3, 4, 5, 6, and then 2 continue. Okay, so it repeats here. So obviously, this is irregular counter. Okay, this is we are missing the 0, 1 at the beginning of the sequence here. We are missing that, and we are missing at the end of the sequence 7. So it's a regular counter. Now, how many flip-flops I need? Well, let's see. How many counting pattern I have? One or codes. 1, 2, 3, 4, 5. 5. Okay, log base 2 of 5 ceiling. That means I need three flip-flops. Let's assume they are Q2 as always, Q1 and Q0. Okay, uh, next is what? Construct the state diagram. Construct the state diagram. Okay, so state diagram. We will start at counting 2, 0, 1, 0. Then next is what? 3, 0, 1, 1. And then next state is what? 4, 1, 0, 0. And then next state is what? It is 5, okay, 1, 0, 1, and then next state is what? 6, okay. Um, let's see. Uh, yeah, I think I'm moving correctly here. 1, 2, 3, 4. Yeah, okay. Next state is 6, and then we go back to 2. We go back to 2. Notice here, after I go back to 6, I go back to 2. Okay, so that's the state diagram. Next is what? State table. Minimization of the input of the flip-flop or JK flop we are using, and construct the circuit. Okay, same design process. Okay, so we're gonna leave it at this point. All right, so because you know now the other steps. Suppose I have another design sequence that says no, we'd like to do this design sequence, which is 2, 1, 4, 3, 7, then repeat 2, 1, etc. Okay, so this is more of really a random. This is more of a random. This is more of a random sequence. So let's see how many codes I need. 1, 2, 3, 4, 5, which means I need 3 flip-flops. And let's assume those 3 flip. So log of 2 for 5 codes. Get the ceiling. Okay, equals 3 flip-flops. Let's assume they are Q2, Q1, Q0. Okay, so let's construct the state table. 2, okay, which is this code here. Okay, you know what? Let's use a different color here. Okay, So Q0, let's use, okay. So the first state here is what? 2. 2. Then next state is what? 1. Then next state is what? 4. Then next state is what? 3. Okay, so let's see. Go back and down here a little bit, make it easier for us. All right, so this is 3. The next state is what? 7. Okay, the next state is 2. Go back to now to the initial state of 2. So this is the state diagram, much like we have done for the previous example. Okay, and then what? Well, and then state table, minimization of inputs, using citation table to get the inputs, minimization of inputs, and construct the circuit. Okay, we're not going to continue with the examples because I think we have gone through really enough details where you can carry on with the rest of the process yourself. So we just illustrate the hardest point, which is getting the state table, the state diagram correctly. Because if you in the assignment or the exam start with a wrong state diagram, the whole problem solution is messed up. So be careful with the state diagram because they set the tone for your answer. Okay, all right. So now what we have is that we have explained the irregular design using the general design procedure of sequential circuit. We have a simplified method. So let's talk about the simplified method. Okay. So the simplified method says uh, we would like to let's for example use example of 3 flip-flops Q2, Q1, and Q0 under a regular count sequence. So we count from, let's say we start from 0 0 0 0 1, sorry, 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, and then you notice that this counter goes back and start at 0. Okay, we are going to present a simplified method for irregular counter. Simplified irregular counter. Now suppose, for example, I want to stop the counting at a number other than. So now notice that here I have, let's see, how many flip-flops I have? Well, m equals 3. And that's why my final sequence is what? 2 to the m minus 1 for regular counter, which is equal 7, which is where I stopped here. Well, suppose my final count, I want to stop at n, which is not 7, some number. Let's say 5. N equals 5. I want to stop at 5, and then after 5, roll back the counter to initial state. So then what I have to do is that I need to catch the condition of n plus 1. What's the condition of n plus 1? It is 6. It is when Q2 equals 1, Q1 equals 1, and Q0 equals 0. So we will let the counter go to n equals 5, and then when it reaches 6, immediately we will take the counter and goes back to initial condition, some initial condition. Okay, so it will not see the count of n plus 1, it will not see 6, because this will happen very quickly. So what initial condition will take it? Well, it depends. Suppose I want it to go back and start counting at 1. Okay, so basically what I am trying to design here, a counter that counts from 1, 2, 3, 4, 5, goes back to 1, 2, 3, 4, 5. So the stop condition for me, the stop condition here is 5. The start condition for me is what? Is 1. So the start condition will help me to do what? Once I reach the stop condition and I'm going to the counter flip-flops and do immediate set and clear and set. Immediate clear or set. So let's say, for example, this is my counter here. And I'm not going to connect it, the connection of the flip-flops for simplicity. I know now you know the connection of the flip-flops, so I'm not going to make the diagram busy. But what I need to do here, I'm going to use 2 inputs for these flip-flops. Okay, for these flip-flops. One input is clear, and the other input is set. So this is asynchronous set and clear. Clear and set. Clear and set. Okay, and this is the rest of my counter. Here is T0, and here is Q0, here is T1, and here is Q1, and here is T2, and here is Q2. I am not going to do the other wiring of this design for simplicity. Okay, I know how to design these. So basically I am using a design of regular counter, and I know for regular counter we have done it before. Okay, that here I connect this to 1, and I connect this to T1, and I connect this here and this here to an AND gate, and this AND gate goes and connects to T2. Okay, I know that. Now, of course, I do have here a clock, and here is a clock, and here is a clock. Okay, so keep this in mind because this is synchronous design. Okay, now I want to focus on my stop condition. How do I implement the stop condition? Notice that my counter here, my counter design, it should stop at 5. We say that we detect the in plus condition, which is 6, which is when Q2, 1, Q1 is 1 and Q0, 0. How can I do this? Well, very simple AND gate. Okay, so here is Q2, and here is Q1, and here is Q0 prime. And remember that I can get Q0 prime from here. This is Q0 prime. This is the stop condition. Okay, then what? Then I need to activate, notice I need to go back all the way to this sequence, which is 0, 0, 1. So how can I set a 0 here? And how can I set a 0 here? And how can I set a 0, a 1 here? Well, I can set a 0 here if I can activate the clear condition. Okay, so let's see. So I need here a 0, and I need here a 0, and I need here a 1. So how can I do this? I can do this by the following. First, I need a NAND gate, because when this is detected, this condition, this becomes a 0. And then I take this line. For this flip-flop to become a 0, I need what? A clear signal. So I connect this to the clear signal. Here I need the 0 for when I go back. So I connect this to the clear signal. So, and here I need to set a 1. So I connect this to the set 1. So watch what happens. When the counter reaches 1, 1, 0, okay, so this is 0. Okay, then this line becomes a 0. And we go to these flip-flops and we clear them and set them to 0, 0, 1, which means it will take me back to the initial condition. Okay, so again, notice This simplified method depends on, we determine the start condition, we determine the final condition here, or the stop condition, we add 1 to it, and we detect it with a NAND gate, and then we connect it to the flip-flop based on what I need to the start pattern. If the flip-flop has to become a 0, then I connect this line coming out of the NAND gate to the clear. If I need a 1, I connect it to the set for that flip-flop. So if for example, if I'm going back, let's say for example, if I'm going back, let's see, for example, if I'm going back to 0, 0, 0, for example, then I will connect this line to the clear signal of all these flip-flops. If I'm going back to 0, 0, 0, okay. All right. So this is now, what are the conditions that I can use, under which I can use this solution? The condition, first of all, I must have a counter. Okay. All right. I must have a counter. And not any counter. The flip-flops must be equipped with a set and clear conditions. So you see how these set and clear here, set and clear. The flip-flops they have set and clear. Also, the counting sequence must be within one step. One step. So in other words, I cannot do random sequence. Okay, I can do one step which is missing some initial conditions, okay, and final conditions, and therefore I can go and modify my regular counter with this NAND gate and using some clear and set, so that I can play with the start and stop sequence or states of the counter. Okay, so in other words, the simplified method is not applied in all the cases of irregular counters. It's just applied for a special class, but it seems to be very straightforward and simple and easy. Okay, all right. Now, finally, what we have, we have the final. We have the final topic here, which is very small, which is the frequency divider. Frequency divider. So, let's say, for example, I have a counter here. All right, and this is my clock to this counter, and here I have Q0, and here I have Q1, and here I have let's say Q2, for example, and let's say I have here Qn. Suppose that the frequency of this clock, is FCLK. It turned out for counters that I can relate the frequency. These are wave-like shape. These counts they behave like waves, and the frequency of the wave that is coming from Q0 equals the frequency of clock divides by 2. And in fact, the frequency of of Q1, if I use it as a wave form, it is equals to the frequency of clock over 2 times 2, which is equals 4, because it is this Q is half of CLK, and this one is a half of that. Similarly, the frequency of Q2, Q2 is half of Q1, so it is equal the frequency of CLK over 8. Now, let's look at the general form. So the frequency of Q over N equals the frequency of clock over 2 N plus 1. Okay, so that's the general form for the frequency of signals coming from these output of this counter. So this is a counter and a synchronous counter. Okay, And if we can borrow some of the waveforms here in the lecture has nice neat waveforms. Um, so if we look at the if we look at the some of the waveforms. Okay, so you can see this is the clock that is input to the counter. This is the behavioral of Q0. You can see that Q0. If this is for example the period for the clock, you can see that the period for Q0 is double that. Okay, and you can see the period of Q1 is double the period of Q0, which is double the, and you can see the period of Q2 is double the period of Q1. Okay, so now you can see that how these frequency are being divided. Okay, the system has duty clock of 50%. What's a duty? What's a duty cycle? A duty cycle is the percentage of time that I am high and the percentage of time I am low. We would like to have a percentage of time duty cycle of 50%. Well, it turned out that the counter provides for me a duty cycle of 50%, and which is great, awesome. We like that, which is very good. Okay, we like that. So the counter really not only it divides the frequency for me with Q1 and with Q0 and Q1 and Q2, it also provides a good duty cycles, which means the percentage of the time when the output is high is equal to the percentage of the time when the output is low. Okay, all right. So this is the last topic of the counter lectures, and we'll see you. We'll talk to you with other lectures. Thank you very much.